Hi, I'm Sai Potana, founder at Embedded Systems AI LLC. This presentation is about vLLM system architecture. vLLM essentially turns LLM serving into an operating system problem, managing memory, scheduling compute, and scaling across hardware efficiently. Section 1 describes end-to-end request flow. A client sends a request using an OpenAI compatible API, typically through a load balancer into the vLLM server. The request enters a life cycle. First, it is received and queued by a scheduler, and then comes the prefill phase. This is where the full prompt is processed and the initial KV cache is built. After that, we enter the decode loop where tokens are generated one at a time. Finally, tokens are streamed back to the client in real time. This pipeline is designed for asynchronous execution, enabling high concurrency. Section 2 describes core vLLM engine that usually resides inside a GPU node. It contains the model weights, the page attention kernel, and other transformer kernels like MLP and normalization. The KV cache manager plays a critical role. It stores attention states as fixed size blocks in GPU memory. A block table maps logical sequence positions to physical memory blocks. The key idea here is that attention operates over these blocks instead of contiguous memory. This enables efficient memory usage without changing the underlying model computation. Section 3 describes scheduler for continuous and iteration level batching of input queries. This is where vLLM differentiates itself, the scheduler. Traditional systems batch requests statically, but vLLM uses continuous batching. At every decode iteration, requests can be dynamically added or removed. This allows mixing of prefill and decode workloads in the same batch. The result is maximum GPU utilization. The GPU is almost never idle. This directly translates into higher throughput and lower latency per token. Section 4 describes memory system, the paged attention, and block management system. The memory system is a core innovation. Instead of allocating large continuous KV caches, vLLM breaks them into small fixed size blocks. Each request maintains a logical view, while physically these blocks are scattered in GPU memory. A block table handles the mapping. Additionally, block sharing is used for sequence with common prefixes using a copy-on-write strategy. This eliminates fragmentation, improves memory utilization, and allows many more concurrent sequences. Section 5 describes distributed serving for large models with like 100 billion parameters. To serve very large models like 100 billion parameters, we need distributed execution. Model parallelism is used to split the model across multiple GPUs. This includes tensor parallelism and pipeline parallelism. Communication between GPUs is handled using high-speed interconnects and collective operations. This allows the system to scale beyond a single GPU or a single node. Without this, large models simply would not fit into memory. Section 6 describes key optimizations in vLLM. On top of the core architecture, vLLM includes several optimizations. Quantization reduces memory footprint and improves throughput. Prefix caching reuses previously computed KV cache for repeated prompts. Chunked prefill allows long prompts to be processed efficiently. Speculative decoding reduces latency by predicting tokens ahead of time. Optimized kernels like flash attention maximize memory bandwidth usage. Together, these optimizations significantly improve real-world performance. To sum up the presentation, LLM serving is fundamentally a system problem, not just a model problem. Memory, scheduling, and distribution are the real bottlenecks. vLLM addresses all three. Paged attention solves memory inefficiency, continuous batching maximizes utilization, and distributed execution enables large-scale models. The result is 2 to 4 times higher throughput with the same hardware. This is what makes serving 100 billion plus parameter models practical in production.